In this video, we're going to start to look at the different type of catalytic mechanisms that are common in biochemistry. And these mechanisms are generally done by enzymes. So to begin with, we're just going to look at the different types of mechanisms you might see in biochemistry. And first, we're going to look at acid and base catalysis, and we're going to look at that by looking at the mechanism of a ketol to enol tautomerization. So if we have a ketol that looks like this, what can happen is that we can switch to an enol by having the carbon and oxygen here. The oxygen takes the electrons to make it negative. One of the hydrogens then would leave to form a carbon-carbon double bond. And this is incredibly slow if it was uncatalyzed. But we can catalyze this reaction by two different means. The first is acid catalysis. That is, we are transferring a proton to lower the free energy of this transition state. So here we have our ketol, and now we have an acid. So this oxygen is going to take the proton from our acid. Then we have the proton from the methyl group leaving. Then we can get our enol. And after every mechanism or every reaction, we always have to regenerate our catalyst. So here we have our catalyst that's in the base form, getting a hydrogen from water to reform our acid catalyst. So that's general acid catalyst, where you donate a hydrogen. We can do the same reaction by having a base instead. So the base here will be taking the hydrogen from the methyl group, and eventually getting your enol. And again, we have to remake our base, so we have to lose the hydrogen that it got. So that's a general base reaction. You take a hydrogen. And in mechanisms, you can have both acid and base reaction, concerted acid-base catalyst reaction, where you have one part of your enzyme act like an acid, another part acts like a base. And the amino acids that can be used for this mechanism are asp, glu, his, cis, tyre, lyse. And if you know what their side chains look like, that should make sense why they are important in acid and base catalysis. Now we can look at an example of this. Here we have two histidines that are going to be important for this mechanism. And histidine is a good acid and base catalysis amino acid because it has a pKa of 6. And the body usually changes around what parts you're in, but inside the blood, the pH is usually 7.2. So you're right at that range where histidine can either take a hydrogen or lose a hydrogen. So let's take a look at RNA ACE, which is an enzyme that is secreted into the small intestine, and it chops up RNA. So here we have RNA, and his12 and his119 are going to be important here. So here, his12 is acting like a base, taking the hydrogen from the 2' position of RNA. What that does is oxygen will then attack the phosphate, and to do that, his119 will act like an acid and donate a proton to this other oxygen. And you have effectively broken this phosphate bond here, and so 1/2 of your RNA molecule is now free to leave, so you're halfway done. You then have a cyclic nucleotide, so we need to get rid of that cyclic nucleotide, and we need to restore our enzyme back to the way it was in step 1. And so to do that, we bring in water. His119 will take a hydrogen from water to restore its acidic state. The OH of water will attack the phosphate, which will break this phosphate-oxygen bond at the 2' position. And the hydrogen that's on his12 will leave and attach back to the 2' oxygen. When that happens, you are restoring your enzyme, as shown here. You're other nucleotide is restored back, so that's free to leave. And now you have an empty pocket waiting for the next RNA molecule to come in to be chopped up. So that's the mechanism of RNA ACE A. Now, another type of catalysis we'll see often is covalent catalysis, and that's when your catalyst actually forms a covalent bond to your substrate. One type that is common is nucleophilic catalysis, where on your catalyst you have a nucleophilic group, and a nucleophile is a group that is donating electrons, and this will react with an electrophile group. An electrophile group is one that's accepting electrons. So here, if we look at our mechanism, we have an NH2 and a carboxyl group, and our enzyme here can be a base where we take a hydrogen, and we can also have an acidic hydrogen here that could also be part of our enzyme. So here, the hydrogen's being taken away, then we're donating a hydrogen, you're forming a covalent bond, and you're forming eventually a Schiff base. And you'll see a lot of times throughout biochemistry the formation of these Schiff bases, and a lot of the times maybe the nitrogen here would actually be part of your enzyme, and you're forming a covalent bond between the nitrogen and the carbon of your substrate. And we can take a look at that for the reaction of acetoacetate going to acetone. And so at the top we have our uncatalyzed reaction, where at first we have a decarboxylation event, so we lose the CO2. We're making an intermediate of enolate, then an acid has to come in and form acetone. So that's a very slow uncatalyzed form. Here, let's look at the catalyzed version, and our catalyst is going to be this RNH2 group. So imagine that this was like a side chain of an amino acid connected to a giant enzyme. And so the first thing that the enzyme does is that we have to kick off this oxygen here, and we form a covalent bond between our enzyme and the substrate, effectively forming a Schiff base. Once we have a Schiff base, then we can have decarboxylation, where we have a positive nitrogen here, so it's going to take the electrons, or the withdrawal of electrons from the reaction center by the now electrophilic catalyst. So that's what's going on here. That's what step 2 is. Then, once our CO2 leaves, then the nitrogen can come back down. We're going to get rid of this carbon-carbon double bond. We also have a hydrogen coming in to make this CH2 a CH3. Then, the next step is we have to get rid of this catalyst. So usually water is going to be doing this step. Water can come in. Kick off our enzyme, so break this Schiff base, break this double bond, restore our enzyme or our catalyst back to the way it was, and make acetone. So see here, we're doing catalysis by forming a covalent bond, and that is speeding up the conversion of acetoacetate to acetone. Now, in biochemistry, since we're generally working with amino acids, we don't have the wide breadth of nucleophiles and electrophiles as organic chemistry does. Rather, we just have a few substances. So nucleophiles are negatively charged or have unshared electron pairs that form covalent bonds. So you're looking at hydroxyl groups, sulfhydryl groups, amino groups, and imidazole groups. And hopefully when you're looking at these, you're thinking to yourself, what amino acids have these side chains? While your electrophiles are usually positive charge, or they have unfilled valence electron shells or electronegative atoms. So you have protons, metals, carbonyl carbons, and cationic amines, or the Schiff base again. And for these nucleophile and electrophile groups, you're looking at lyse, his, cis, asp, ser. They're all good covalent catalyst. And we'll see once we start looking at mechanisms, these amino acids popping up and forming covalent bonds with our substrates. But that's it for this introduction, and I'll see you in the next video.